Welcome back everyone. So today we are going to discuss about equipotential surface. So this will conclude our electric potential and then we will move to electric potential energy. Okay. So what is an equipotential surface? So here you can see, suppose I am having a surface, maybe it's a spherical one, and of course consider it in 3D. Okay. And let us consider 2 to 3 points. Suppose this is point A. Okay, this is point B, this is point C. If all the points within the surface are of same potential, means at point A, VA, at point B, VB, and at point C, VC. At all the points, if potentials are same, then it will considered as equipotential surface, provided we need to consider it as VA equals to VB equals to VC. So at all point on the surface, the potential must be equal. Okay, which potential? Electrostatic potential. Got it? So this is basically equipotential surface. So here two types of question will come. One, you need to draw some diagram. Okay, and second thing, you need to do some numericals or some aptitude type of or conceptual type of question on the basis of the properties of equipotential surface. Okay, so first we will learn how to draw equipotential surface. Like for a point charge, we will consider 2 points here. So first we will draw the equipotential surface for a point charge. So suppose here I am placing a small q charge. Okay, so around it, if I consider a circle or concentric circles, then each of them will be equipotential surface with respect to Q. Now here you have to notice two things. Number one is, suppose for this particular sphere or circle, if I am considering in 3D, then sphere, in 2D, then circle. Okay, this suppose this is of radius r, this is of 2r, this is of 3r. Now this is having a particular potential and within which all points are having same potential. Here also the radius is 2r, right? This is of radius 2r and this is our potential surface, equipotential surface. Here all the points are of same potential, but these two surfaces are not considered or equivalent in case of potential. They are having different potential, but all the points within which are equal. Suppose these 2 points are equal. Okay, let me change the color. Suppose here these 2 points are equal, and for second one these 2 points are equal, for third one these 2 or 3 points are equal, but these 2 points cannot be equal. We need to consider spheres of different radiuses. They are called concentric sphere if they are sharing same center, and at the center you need to place a charge. For this charge, these are different equipotential surfaces. Okay, now note two things. Number one, if the distance from the center is increasing, then the radius is also increasing. Now how the potential vary with radius? Inversely. Now if the radius is increasing, then this will decrease, right? So we can say for this surface, if the potential is 100 at all the points, for this surface the potential may be 80 for all the points. For this surface the potential may be, for the larger one, the potential may be 60. While you are going from the center towards outward, then of course the potential will decrease. The value of the potential, the strength of the potential will decrease. So this is for point charge. So what will happen to line charge? Suppose I have taken this one. This is equivalently charged with a positive charge. Okay. Now let me consider a cylinder across it. So this will be the line charge distribution of an equipotential surface. So for the similar thing, if we consider concentric cylinders, then here also we can say 2 to 3 cylinders we can consider which are concentric. Then also we can say these are also equipotential, all 3 of them. Okay, so these basically how equipotential surface looks like. Okay, next is about the properties. So we will discuss 4 properties here one by one. First property is, see, suppose this is equipotential surface. Here you have point A, consider it as VA, and here it is VB. This is point A, this is point B. Okay. Now if the value at point A and value of point B is equal, then what will be the difference? 0. Right? So here it is only written the potential difference is 0 between 2 points in same equipotential surface, on the same equipotential surface. Okay. So this is our first property. This is very easy one. Second property, and of course one of the most important properties of all, that is the work done in moving a charge will be equal to 0 in a equipotential surface. How? Again you see here a point A and point B, right? Very good. So we have considered VA minus VB equals to 0. Another thing you know that VA minus VB is basically what? W, work done by charge, right? So you can say if this value is 0, then W equals to also 0. If W equals to 0, hence it proves the statement. That is, work done in moving a charge within a equipotential surface will always 0. Again I am showing you, if VA minus VB is 0, then of course W by Q, this ratio will be also 0, because we know VA minus VB equals to W by Q naught, right? So if this is 0, we can say that W equals to 0. So to move a charge from point A to point B, suppose I am taking a charge here and I am moving it from point A to point B, so I am doing no work at all. This is property number 2, very important. Third property, see, this property is very much beautiful. So we have already learned this equation, right? Just previous class we have learned this, right? Okay, dot product, if I am doing this dot product, then I will get the scalar. That's why I have given vector sign here and not here, right? Get it? Now this is what? Difference between, that is potential difference between 2 potential points within an equipotential surface. So that is potential difference. So if I am making this 0, then E equals to minus E dr, dV equals to 0 equals to minus E dr, right? So here I am having 2 things. Number 1, how this left hand side can be 0. Number 1, if E itself will become 0. Number 2, if the dot product, if I am breaking this dot product, I will get E dr, of course with a minus cos theta, right? So if cos theta equals to 0, then theta may be equals to 90. So 2 points to be considered. If E equals to 0, then potential must be 0. Other than that, it should be 90 degree. It should be perpendicular. It should be perpendicular. Now let me just give you a nice explanation of this. So this is your equipotential surface for a charge Q, right? So let me draw the field lines for plus Q. What will be the field lines? Like this, right? So what are the angle produced by this? 90, 90, 90. Everywhere you look at, it will be 90, right? So here you can say that if you just break this E dot dr, here it is always 0. Then E dr cos theta, right? So this cos theta will become 90 degree to make it 0. So in this way we can understand the third property, that is electric field lines are always perpendicular to the equipotential surface. Okay, this point is also very, very much important. Last point, which is two equipotential surfaces never intersect each other. Okay, what is it? It will be a space. Anyway, so two equipotential surfaces never intersect each other. This type of statement you have already learned in the first chapter, that is, two electric field lines never intersect each other, right? Here you have drawn, there you were drawn that explanation that if two electric field lines intersect each other, then at this point there will be two different direction of E, right? So it is impossible. If we do so, if we just cross two field lines, it's impossible to have two different direction at a single point of electric field, right? So the same explanation we will give here also. See, let me consider two equipotential surface. This is surface number 1, this is surface number 2, right? For surface number 1, what will be the direction of electric field? Just we learned in the previous slide, it will be perpendicular. So in this direction, this is for surface number 2, right? This will be the perpendicular direction. And for surface number 1, this will be the direction of electric field. Okay, let me just clear it once again. This will be the direction of, yes, this will be the direction of electric field for surface number 1. Right? So at this point, suppose I'm considering it at O, at point O, we are getting two different direction for E. So for the same reason, we will cancel this out. We will cancel out this thing. So we will say that two equipotential surfaces never ever intersect each other. So have you understand the point? If they do so, if they intersect each other, then of course we need to have two different direction at a single point. For the electric field, that is impossible. So we cannot do that. Now last thing we need to discuss here, that is equipotential surface for a dipole. Here, so I am taking plus Q and minus Q charge. Okay, first you need to draw the field lines. So what will be the field lines? Like this, repulsive from there here and attracted towards Q, minus Q, right? So let me make another one. At this side it will be like this somehow, and from this side it will be attracted, right? Now let me draw the field lines for you. See how the equipotential surface, how the equipotential surface should be made. It should be perpendicular to the direction of electric field. Now here if you can see, all of them are almost parallel to each other. So we will consider it as they are parallel to each other, we are saying, then it must be somewhere at this narrow region, at this much narrow region, they must be straight line. So here we can consider a straight line which is perpendicular to the path, to the direction of electric field. Here you can see, right? Another one. For this particular point, this will be the direction, this will be the direction, this will be the direction. Now if I am bending it towards here, then it will complete. Again if I am doing it, then, so you can see the pattern. Here also if I am doing this, this will be, I will attach the clear picture of course. So here you can see that here at this point the lines are pretty close, pretty near, but at this point the differences between lines are larger. So this is the correct way to draw electric field lines. Okay, I am just pasting a beautiful picture of it, that is here it is for a dipole. Okay, this is most important, and maximum time if any drawing is coming within this, then only this picture will come. This is for two like charges. Here they have taken two positive charges, right? So this will be your equipotential surface pair of like charges, and this is equipotential surface for a dipole. So up to this, thank you for watching.